Hello, my dear students, and welcome to our first technical lecture with this electronic measurements and instrumentation course. Today, we are going to start with this together, a first stage out of 12 stage during this electronics and instrumentation course, electronic measurements and instrumentation course. And as I mentioned in lecture number 0, our start will be directed toward the measurement systems and the measurements error. And I think that this is a fundamental lecture toward understanding the basics of electronic measurement systems and different types of errors and how we can deal with these types of errors. As we will know during this lecture that we cannot ignore errors, we cannot cancel errors. However, we need to just understand and deal with errors. So let's start our first lecture under the title of Introduction to Measurements and Measurements Error. As I mentioned in lecture number 0, we will keep using David Bell reference as our standard text book, where we are going to start with chapter 1 here. And additionally, you can find more useful electronic materials, either using MIT open courses or even using UC Berkeley. You will find, I will provide you through the e-learning a series of interesting links that you can visit in order to go deeply with this content. Okay, so let's start from the beginning with asking what is a measurement. Generally, we define it in lecture number 0 when we say that a measurement is a process of converting a variation of a certain phenomena into a sort of electronic variation. So, for example, when you measure the temperature, so the idea here is you are going to detect the variation of temperature and then convert this variation into a signal that can be understood by the electronic circuit. So a signal that can be understood by an electronic circuit is either a variation in current, a variation in voltage, a variation in resistance, a variation in capacitance, something that can be then processed in an electronic format. What are the characteristics for a measurement? So here you can find 3 main characteristics that should be associated with any measurements. The measurement should be descriptive, selective, and objective. So what are these 3 parameters, or what are these 3 characteristics? Descriptive, so it should describe something. For example, when we measure temperature, we are describing the temperature. We are trying to observable property here. We are trying to observe the temperature. So the first keyword here is to describe something. Otherwise, it doesn't include any information. The second is it should be selective. I'm selecting because our nature, our environment is surrounded with a huge amount of phenomena. For example, we have temperature, we have noise level, sound noise level, we have humidity, we have wind speed in outdoors, we have light intensity or solar intensity if we are outdoors. These are a lot of phenomena around us environmentally that can be measured. So you should select one of these phenomena, a single selective phenomena that should be measured. So that's the second property associated to measurement. And thirdly, it should be objective. What I mean here by objective is it should be independent on the observer. So for example, if I pick 2 different sensors or 2 different instruments, or even for the same instrument, if 2 people are monitoring this, they should reach up with the same value of temperature. So here it's an objective property or objective characteristic of a measurement. So generally, a measurement should be descriptive, selective, and objective. Okay, this is a very simple block diagram that we are going to use a lot during this lecture, considering three main blocks with surroundings. The first is the measurement object. Again, it can be an environmental, something like temperature. It can be gas, it can be biomedical, it can be light intensity, it can be a percentage in a chemical component, whatever it is. So you are measuring some object. So this is the first block. The second block is the measurement system, where we can globally call it measurement instrument, or specifically we can call it a sensor. And the third is the observer, the one who is going to catch this signal and process and read and so on. These are the three main blocks describing a measurement. But regardless of these three blocks, we have associated parameters. For example, the environmental effect. So, for example, when you are measuring the temperature, you can measure temperature at different humidity level. So, does the variation in the humidity impact your measurement system? So here the environment can impact your measurement system. And accordingly, it can introduce some sort of error or variations. So the environment is one of the factors that can impact your system. And alternatively, your system might impact the environment. For example, if you are measuring something using a coil with a current flowing in a coil, so you have an instrument, and this instrument may include a coil, an inductor, while the current is moving in a coil. And this, using our basic information, we can understand that when a current is moving in a coil, it produces some sort of an electromagnetic waves. Herein, if there is another device in the same environment, this device will be impacted by the electromagnetic waves produced from your device. So it's a bi-directional process. The environment can impact your measurement system, and your measurement system might impact the environment. As you can see here, these two directional errors. Another important thing, maybe we are going to introduce it here as well, is that the bidirectional process in the correlation between these two blocks. So sometimes, which is very you can commonly understand, if you would like to measure the temperature inside a furnace, and you buy a temperature sensor and you insert it into the furnace and you monitor the reading. If the temperature of the furnace exceed the limits that can be resisted by the circuit measuring the temperature, your measuring object, which is the temperature, will impact the measurement system. So you might destroy the temperature, the sensor or the measurement system, because simply you select a wrong sensor, which, for example, can measure a temperature up to, let's say, 200 Celsius. However, your furnace is reaching, for example, 700 Celsius. Definitely your sensor will break down. So herein, the measurement object influences the measurement system. Additionally, on the other side, if your sensor is not well designed, it might impact the measurement object. So let's make it in the other round. If you are using a temperature sensor, and for some technical problem, the sensor circuit starts to be heated, its temperature increases, and you are basically measuring temperature. What will happen is your system here, your measurement system, will impact the object and you will read a higher temperature. So it's not the temperature of the object, it's simply the temperature of the system itself. So that's why here you can see this red arrow. Again, the measurement system might affect the observer. So, for example, if I'm not a calibrated sensor, then you will get a reading. Here you can find this delta Y, which we are going to describe it in very detailed manner in the coming slides. This delta Y will appear due to a certain error. So I am an observer. I will be impacted by a reading which is not correct because simply there is some sort of error or it's not a calibrated sensor. And on the other hand, if I am not well trained in using the sensor, I might impact the sensor. So for example, if I inserted in a wrong way, if I inserted in a wrong configuration, so now the observer influences the performance of the measurement system because, for example, he is not well educated how to use this sensor or whatever the reason is. And it's very important to monitor these delta X and delta Y because we are going to consider this here under the title of the sources of error. So as you can see here, the source of error might be in the object itself, might be in the sensor, might be in the observer. These types of errors we are going to we are going to consider it in the next half of this chapter. So as you can see here, the measurements must not be affected by the observer. It should be absolute measurement, and this is also our target to try to do our best to guarantee that our measurement is isolated. And on the other hand, we are trying to minimize the impact of the surrounding effects, either from the observer, from the object, from the environment. Definitely, we will not be able to do it. This is a hypothetical model, but the minimum effect, the better measurement. Okay, generally, we can define the level of measurements into 7 levels. And this is very famous way to define measurements. It's a very, very old theory related to Stevens in 1946, when he starts to define scale into 7 different levels, starting from nominal, ordinal, interval, ratio, and absolute. What we are going to do is we are going to scan these 7 alternatives and try to see what are the differences between these from these alternatives. Let's start with the basic foundational way, which is the nominal scale. In order to understand the nominal scale, I need you to have a very basic background about any type of sports, let's say, for example, football, because it's the most popular sport all over the world. Definitely, all of you know that, or not definitely, but let me assume that all of you know that a football team consists of 11 players. Each player has a number on the backside of his t-shirt. This is a type of a scale, believe it or not. You can tell me, but these numbers are random. So a player can wear a t-shirt with number 1, number 2, number 8, number 9, number 32, number 26, number 28, whatever the number it is. So how come this is a scale? It's a random number. It's a random number, yes, but there is a restriction on this number. Anyone know what is the restriction on this number? Simply, the restriction is it is forbidden to have 2 players wearing the same number. So choose whatever number you want, but we shouldn't have, or we shouldn't observe 2 states, 2 numbers with the same value. This is what we call a nominal scale. So for example, if you turn it into a very preliminary digital way with 1 and 0s. So if you have 2 switches on and off, and I told you that this is a nominal scale, what I mean is that what is a nominal scale? So if the first one is on, the second will be off. And if the second is on, if the first is off, the second is on. These are the two possible combinations. But it's impossible to have it both on and both off, because now both have the same value. So that's why we call, or this type of scale is a nominal scale. And as you can see, of course, this is a very foundational, very preliminary understanding to a scale. A next scale is what we call the ordinal scale. The ordinal scale, one of the very basic examples to the ordinal scale is the relation between the decimal value and the ratio value. For example, I give it here for the power. So if you have a power in watt and you need to convert it into a decimal, I think you already know this information, that it's the dp, the power in dp is simply 10 log the power in ratio. Now you are creating a conversion scale between a linear scale, which is the power, to a logarithmic scale, which is the dp scale. So you can fund it like that. If I have a state A and state B, so let's call this A and this B. After conversion, the distance or the gap between these two values will get closer, because you are transferring from a linear scale to a logarithmic scale. So for example, if you are comparing 100 watt with 1 kilowatt. So in the linear scale, it's 100 to 1000. In the logarithmic scale, 100 will turn to 2, because 10 log, log 100 with 2, so 2 times 10 will be 20, and 1000 will turn to 30. So in the linear scale, it's 100 to 1000, but in the logarithmic scale, it's 20 to 30. Basically, the gap between 20 to 30 is less than the gap between 100 to 1000. So here, you decrease the gap between state A and state B by this conversion. However, you keep the order. That's why we call it ordinal. So still state B, if we assume that B is on the right, so still state B is higher than state A, but with a less difference. This is what we call an ordinal scale. So here, this is a wrong example, because we start with A and B of the same level. It does make sense after conversion to get B less than A. This is wrong. So it's still in the ordinal scale. You should keep the order, regardless the gap between the two states. And that's what we call the ordinal scale. The next one is the interval scale. And again, an example, which I think you already know, which is the transfer of the temperature from Fahrenheit to Celsius. And here, as you can see, my dear students, it's a linear relationship between temperature and between temperature in Celsius and temperature in Fahrenheit. So it's a higher level of an ordinal. It still is an ordinal, but with a linear transformation. And that's return me back to the this staircase example. So it's, as you can see, it's an accumulative. So whenever you are an ordinal, you should be nominal. Whenever you are interval, you should be ordinal and nominal, and so on. So when we are considering nominal scale, we are considering here a variation that's ordinal, but ordinal in a linear way. So simply, this state A, B, C, D, when I transfer it back, you can see that there is a ratio of transfer. So it's when the ratio between A and B increase, the similar ratio which increase between C and D. So because this is a linear relation. However, this is a wrong example here because it doesn't change in a linear way. And this is what we can call the interval scale. Another type of measurement is the ratio scale, which is still linear, but just just as an absolute. So the equation, instead of having equation y equal mx plus c, it becomes y equal mx. So as if c is equals to 0, which is simply the conversion of units. So when we convert from millimeter to centimeter, from centimeter to meter, from meter to kilometer, and so on, you are just multiplying by a factor. So as if you are just multiplying y equal mx. So X is the input, Y is the output, and M is a ratio. You are scaling between these two scales. And this is a ratio. And as I just said, a ratio scale is by default an interval, an ordinal, and a nominal scale. So this is typically the example. Finally, we have the absolute scale, which is unchangeable. Example for that is time. So time is an absolute scale. You have or you monitor the time in a certain way, which cannot be converted into another structure. It's an absolute value. So this is an example of absolute temperature, sorry, absolute measurement. So as you can see, it's A and B. So for example, if the clock here, for example, now the clock is 10:41 a.m. morning in Egypt. So it's 9:41 a.m. morning in London. There is no conversions. It will become as it is. You cannot say that in another system, this gap will be 2 hours, or you cannot say that it's 12 in Egypt and it's 11 in UK. It's absolute value. And here my question is, do we have another example for an absolute value? Please try to think and reply. Maybe you can reply in comments, or you can send me an email if you can find something else that can be considered as an absolute value. Okay, so let's go to the next step. And I think this is very this is very known for you. I think I definitely you see this before in the physics classes, which is the SI unit. I think, or I believe that you already know the SI unit for length, mass, time, and so on. So I will not waste your time in this. And here is the definition of units. So one example, when you say 1 kilogram, so this is a 1 kilogram as determined as a certain amount of calibrated prototype of a mercury with 2.3 microgram variation and so on. It's not about, I think you already studied this in physics, so this is not my point, but my point is something very important. And this is mainly, I insert this slide for a single keyword, which is calibration. So any measurement system, including sensors, should have its calibration standards. So, for example, usually maybe in year one year ago, when you were in year one, and I ask you, for example, that okay, your electronics project is to make a temperature sensor. Okay, and you did a very good prototype, the temperature sensor, and you show it to me in the discussion, mostly in the lab 011, and we did this together. And usually, I think I told you a very simple question. So, okay, the temperature sensor is showing now 22 degrees Celsius. How should I trust this value? Why should I trust you that this is now the temperature is 22? So you have to implement a calibration step, a standard calibration step. So one of the very important items we are going to consider in this course, how to calibrate your circuit or your sensor, because this is a very fundamental process for any sensor. Okay, so this is again the SI units, okay, and here, of course, I think also already you know this prefix abbreviations for nano, micro, milli, centi, decimal, kilo, and so on. Again, this is very standard. I will not going to waste my time in that. So again, a very basic, again, as I mentioned, this is a very, very basic introduction. So maybe it's a high level school introduction. So I'm going to be relatively with high speed in that. We have two types of values, what we can call a scalar and what we can call a vector. And this is important when you are doing measurements. So when you have something scalar, this is simply that this is something without a direction. For example, temperature. This is a very good example for a scalar quantity. It's a temperature. There is no direction for that. Math, different parameters. However, we have alternatively what we can call an vector quantity to be measured. So when I told you, please measure the force applied on whatever surface, body, whatever, herein I should expect from you to measure both the value of the force in Newton, for example, and the direction. Or you can say that, okay, this device is going to measure the orthogonal force, which is the force perpendicular on the surface. So you now define in advance the direction of the measurement, and then you define the value in Newton. So this is important when we consider vectors. And definitely, you know that scalar quantities are absolutely added or subtracted. However, vector quantities are added or subtracted with vector direction. So, for example, if I have a vector like this in the in the first quad, and I'm measuring only the orthogonal force, so I'm just measuring this perpendicular component. Assume that this is a vertical. It's not so vertical in the graph, so I'm sorry for that. Maybe the figure is stretched a bit, but assume that it's vertical. So this is the vertical component I'm measuring. So I'm not measuring the red vector. I'm just measuring the vertical blue vector. You can see it here. Again, another important classification for measurement systems. So one of the very important classifications for a measurement system is to define or to classify measurement systems into two types. What we call an active and what we can call a passive measurement system. So when we consider an active, that's mean that internally you are doing or you are consuming some sort of power, energy, in order to do the measurement internally inside your sensor, inside your measurement sensor. However, when we call it a passive, that means that you, in order to do the experiment, you need an external exciter. Let me give you a very simple example on that. If I'm measuring a resistance, of course, this is a very traditional example because nowadays we are measuring everything with the same device, which is multimeter, but let's describe it in an old-fashioned way. If I'm measuring a resistance, then I have two options. The first option is to have a device, traditionally they call it ohm meter, which is connected to the resistance. As you can see here, there is no external exciter. So basically, based on Ohm's law, we know that the resistance value can be measured by applying a voltage, a potential voltage here, and due to this potential, current will move. Then you calculate the value of voltage, the value of current, you divide the voltage over the current, then you get the resistance. This is the basic understandable way to measure resistance. So if we consider it from this way, then this, what we call it ohm meter, a black box, which we call it ohm meter, includes in between a battery that generates a voltage with a certain value and then measure the current, and knowing the voltage value and the current value, it divides the voltage over the current to get the resistance. So basically, this block diagram, which is the ohm meter, includes internally a voltage source or a current source, so that it is capable to induce voltage and current in the resistance and measure the resistance. And this is what we call the active measurement, because your sensor is active. It includes a voltage or a current source. On the other hand, if you buy a traditional voltmeter or current meter, a meter, this traditional voltmeter or ammeter, and by the way, in the next chapter, we are going to study the basics of the ammeter and the voltmeter. So in this way, or in this circuit, we are going to just measure voltage or current. So for example, here, if I bought a voltmeter, which must measure voltage, and I connect it to resistance, it will read nothing because simply there is no current, there is no voltage, so it will read zero. In order to perform the measurement, I have to put a current source, for example. So simply what will happen is the current source will move current into the resistance. When there is current in the resistance, then there will be voltage drop. Then the voltage drop will be measured by my measurement system, which is the voltmeter in this case. So herein, in order to perform the experiment, you need an exciter, which is current source. Of course, you can do it vice versa. So you can insert here a a voltage source, and you can insert an ammeter in series, and you can measure the resistance. So it can be in both directions. So this what we call a passive measurement system, because simply you need an exciter here in order to perform your experiment. Okay, so this for me terminates the first half of the lecture, considering the measurement system. The second portion of the title, if you remember the title of the lecture, it's Introduction to Measurements and Measurements Error. So now we understand briefly what is measurements systems and different classification of different measurement systems. The next stage, or the next half of the lecture, will be directed toward measurement errors, the type of error, how we can demonstrate error, and how we can control errors. So this will be in part number 2 of this lecture. Thank you very much for your concentration, and looking forward for our next part with this chapter.